All right. Let's see. Can we see? No. Yeah. Well, one of you's mind hitting the power button. You can do it, Hussein. You can reach, stretch. I'd say it's the small one. Yeah. Yeah. There we go. Yeah. That's where it does. Okay. Yes, indeed. Okay. Can we have a look at this? So, we actually did a little bit of this when you were preparing the. Oh yeah. Plus, it'll take a second just to fully brighten, won't it? Yeah. Okay. So, we. Let's see. Yeah, we actually did a tiny bit of this when we did the lab report. Do you remember when you had to calculate something called R squared? Yeah? You remember that? Yeah, you remember? And obviously R squared has to be a positive number because it's a square. And we said it's between 0 and 1. Yeah? And I think I mentioned this last time as well. What does it mean when the R has a value of 1?
Because it must happen.
No. Yeah. I'll give you an example, because a normal question in the exam is they give you 4 different graphs and they would ask you to match the graphs to their R squared value. So an example might be something like this here. There's 4 graphs of x and y. And I think it'd be good if you can add this into your notes as well. So I'll do some examples.
Strong positive.
Yeah. Well, I'm not looking at the negative ones just yet.
That's wrong.
Ray showed me.
What?
Ray showed me.
Did he? Okay. Okay.
He's going nowhere.
Okay, so values might be something like R squared equals 0, 1, and 0.8. These are your possible answers. So what do you think this one will have?
1.
This one, well actually that's supposed to be lined up perfectly. R squared equals 1. This one, what do you think?
0.
Yeah,
0.1.
nearly 0 I would say. Yeah, roughly 0. There's no real linear relationship here, is there? This one, we'll say is the 0.8. And this is interesting here. This one's 0. Because the R squared only tells you if there's a linear relationship. So, yeah, even though there might, well, clearly there's a relationship between x and y here, but it's not linear. And the R squared can only tell us linear. Okay. So this is a question I've seen on the exam a couple of times, where they ask you to match up the graphs. Now, we'll do another example in a minute. If you can add these to your notes as some examples.
How did you know, like each, like it is 0 and 0.8?
It's just a judgment. 1 represents a perfect fit, and 0,
Oh,
you know, it's only a judgment, you know. Also, if you like, you can express R squared as a percentage. So you could say this is 100%, 0%, 80%, and 0%. Zoom out a bit. What do you need on the top?
so every time we get like the r square equal to 1 is gonna be perfect, right?
Has to be. Yeah.
In the exam, will they give us the number?
Yeah. Yeah. But they'll make it pretty obvious, like how I did. You know, they're not going to give you one that's 0.8 and one is 0.7. It's going to be clearly a good and a bad one, you know.
Why like 100%?
I'm saying you can change the decimals into percentages. So 1 is 100%. Now, this r squared, yeah? This r squared is not called correlation. I think it can be called coefficient of determination. But we don't have to worry too much about that. We care about correlation, which is very, very similar to r squared. In fact, correlation is just the or. Small, well, we can use small or big or. I think in the exam they use small or, but there's no difference here for us. And you know what, I should actually maybe stick to what they use in the exam. I think they use a small or. So, the relationship is exactly what you think. R squared is just the value of R squared. But the difference is small. The R can now be negative, whereas obviously R squared can only be positive. So the difference is, if I had a graph like this, I could say the R squared is equal to 0.64. I'll just, whatever, just make up. Okay? But the R is 0.8 with a minus. Now you can check it out. If you square this, you do get 0.64. The reason for the minus is telling us that the line is going down. So the only difference is that we can now have minuses, and that can tell us if we're going up or down. So this, for example, is R equal to plus 0.8, and the R squared here is also equal to 0.64. Yeah?
So negative or positive, it just gives us a sign.
Yeah. Yeah, this, I know this has a negative R and this has a positive R. Yeah.
I just like,
So why do we square?
Yeah, I was just about to say that next.
it's very simple.
Like, what's the point in squaring then? Yeah.
Like, I understand.
There is a reason for it. So, as Hazel was just asking, and as I was about to explain, well, why do we bother squaring? Like, what's wrong with just using or by itself, with the positive and the negative? And in fact, you might say, well, isn't it better to keep the positive or the negative, because then we can know if it's going up or it's going down. And the reason is this, if I can scroll down, do you have this drawn? Yeah. Well, I'll just leave it up as I'm explaining. The reason is the R squared actually has an interpretation, if you know what I mean. There's actually something that you can say about R squared that you can't really say about R. It has a meaning, and the meaning is this: it's when you convert it into a percentage. So if I say R squared is 0.8, like, or 0.64, that's 64%. That is a percentage for how well the model, and in this case the model is the line, yeah, not fits a straight line, but how well the model explains you know, it's a good guess, and you would think it would be that, how well it explains linearity, but actually it's something different. It's how well the model explains variance. Now let me explain what that means, okay? Imagine you didn't have the line drawn, and you just had the points x and y. okay? And you pretend you didn't know there was a linear relationship. When you look at this data, you'll see the x will have different values, yeah? And the y will have different values. So, can I scroll down a bit? So let me explain here. So you're looking at this data and you look at your x values and you say, okay, here's my x values. And they're all a little bit different, aren't they? And then let's have a look at the y values. I'll just draw them across. And they're all a little bit different. And you have lots of variation. The x's and the y's can be quite different. Now, the moment you draw a line, you now are starting to explain why the y is different. Why is this y value different to this? Before you drew the line, you had no explanation. They were just different values. But now that you drew the line, you can say, well, these values are different because their x values are different. But you realize, no, don't. Now, okay, I'm banning you from making that sound effect because it's annoying me. If you have a question, you ask me a question that has a verb and a question mark at the end. Okay? Right. Continuing. So as I was saying, if you were to look at the y values before you draw the line, the y values would be different. And you would have no explanation for why the y values are different. So for example, maybe the y values here represent, we'll say, people's weight, or something like this. Okay? You might say, well, why are they different? Well, I don't know. Everybody's is different. But if you knew everybody's height, well, then you can start to explain why y values are different. Okay? Another example. Okay, so imagine you measure people's, like if you're in a hospital and you're measuring patients' blood pressure, or something like this. So every patient will have a different blood pressure. And you have no reason or no explanation why people have different blood pressures. You have one pressure, he has a different blood pressure, and so on. But maybe now you collect their age. And so you can now start to explain why this patient has a higher blood pressure because they're older, maybe. Right? Something like this? Yeah, this is what we're leading into, yeah. So now that you have the x, you can explain some of the reason why these have the values that they do. For example, why does this have such a bigger y value than this point here? Why is this value much bigger than this value? Because the x is bigger. So that's like saying, why is this person heavier than that person? Well, they're taller, you know? Now, will this explanation work all of the time? No. So this number here is how much of the variance you have explained. How much that you have explained. So 64% means you have 64% of the differences explained, but not 100%. So for example, this person here, if it explained it perfectly, then they shouldn't have had a y value as big as this. Their value should have been where? Should have been a little bit less, shouldn't it?
But we can't like describe it without the line from the points.
Not really so much. Like if I just had, suppose I just gave you these y values, 2, 6, 1, 9. Alright, I'll give you some more. Here's an example. 2, 10, 4, 6, 0. Why is the 10 bigger than the 0? Who the heck knows why? But if I gave you the x values, why is the 10 bigger than the 0? The x is different. This one had an x of 5, and this one had an x of 0. And it seems like the y value is twice the x value. And so this explains why you got the values you did. Now let me make a small change to it. Suppose I had this. And 0. I've changed them slightly, haven't I? Yeah. And I'll keep the x the same. Is it true to say that the y is roughly twice the x? Yeah? If the x is 5, what should y be? Should be 10. And what do we have? Yeah. Have I explained everything? No. But I've explained a lot of what's happening here, but not 100%. Maybe this is higher because there's another value. So from a medical point of view, this might be saying, why does this patient have low blood pressure when we know that perhaps they smoke and they drink? Well, then there must be other variables that might explain this, like perhaps they're on some kind of medicine that reduces their blood pressure. You know, or cocaine, yeah. Does this lower your blood pressure? Okay. You get the idea anyways. Okay. So, since you're all going to be studying science in one form or another, this is going to be something I'm 100% certain of you'll do in any statistics class in any medical or biological context. Because a lot of the time what you're doing in medicine is you're looking to explain one thing as a result of some other value. Okay? Why do people have high blood pressure? People are maybe smoking more. Why is there more diabetic cases? People are consuming more sugar. You know, you're trying to explain relationships here. Do you understand? Yeah. So the correlation is a way to measure how strong of a linear relationship there is between two variables. So, what is the formula to calculate that? And then let's calculate it. The formula uses our familiar buddies of the small s's. Small s, oh, and it has your favourite one as well, has it? It's small sxy over sx sy. All small. Yeah. And this could be positive or negative.
Then when we get the answer, we square it, right?
Yeah, or not. It depends on the question. Sometimes they ask for or, and sometimes they ask for or squared.
Okay, if the answer is already like, if they ask for the r square and the answer is already positive, you will square.
Oh yeah, yeah, yeah. Now, can you see now? There is one situation, and only one situation, in which, or I suppose two situations, in which Sxy actually does equal Sx Sy. And what is that situation? Yeah, there is an actual situation where Sxy will really equal Sx times Sy.
When we divide the Sxy by 2?
No.
Oh, when,
No.
if we divide it
No.
by the...
No. No. So look, when the data falls perfectly on a straight line, what's the value of or? 1. And that must mean the top equals the bottom. So only for data that perfectly fits a line can we have these equal. Yeah? Yeah. So if you had this situation where they all lined up perfectly, that means the or is equal to 1, which means these have to be the same. But they're usually not. And how different they are is what's measuring the correlation. In fact, if you look at this, because it has to be less than or equal to 1, which is usually, or which is always the bigger one? No, the bottom.
No, bottom.
The bottom,
Yeah,
yes.
I didn't finish my sentence.
Yeah, okay, yeah. The up, not that, the bottom. Yeah, okay. That was what you were about to say. Yeah, okay. Right, so let's have a calculation as an example. We'll just pick a few data points so that we don't have too many. Can I scroll down? As an example? Yeah, so I'll just pick 4 points. I'll say x could be 0, 1, 2, 3, and 4, like this. And we'll say this is 0. No, I'll say 5, 11, 12, 15 then, okay, fine. Yeah, there. Right. Oh, sorry, did you write down this formula here, yeah? Okay. So, small sx, that is the sum of x squared over 5, isn't it? Yeah, I think so, minus the average squared and then square root of that. Yeah, so let's calculate that here. Yeah, well, I'll write it down here. So the first one over 5, that will be 1 plus 4 plus 9 plus 16, isn't it? And then minus, and then this will be squared over 5. And what's that? 4, 5, 6, 7, 8, 9, 10. Oh, that's 2, isn't it? So that's minus 4. And then this is 5, and 9 is 4. Is it 6? Yeah?
Yeah, 6.
Okay.
It's 6 because when you add them and divide by 5, right? Yes.
Yeah.
Wait, how did you get the 1496?
Which one?
Wait.
The squares. Yeah. Okay, next. Let's get SY now. Oh, 25 plus 121 plus 144 plus 225 over 5 minus, what's that, 27, 38, 43 over 5, is it? I don't know. Can you calculate this one, please? 25, 121, 144, 225.
1 to 1.
Root 103.
Yeah.
The average of y. 5, 11, 12, 15 over 5.
73.96.
Is what, the average?
Yeah.
So 17 point.
73. 73.9.
So what's the final answer after the root?
Wait, my brain. Okay.
5.388, is it?
Yeah.
Yeah. Okay. The last one, yep.
How did you get 25?
5 squared. Yeah.
But
No. Yeah.
in here, these formulas, there is like negative square root.
Yeah. That's right. That's right.
No, I mean, why there is like y?
That's y average. Yep. Okay. Now I'll need your help with the SXY. What's that one? That was sum x, isn't it?
Yeah.
Sum y over 5, isn't it? Yeah. So the total x times the total y over 5 minus the two averages, isn't it? That's 2. Oh, what was the average for y? 1.7, was it? No, 17 point something.
The average of y?
Yeah.
43
Hussein,
over
do you mind getting me just the average of y here?
73.
And then, oh, you have it. What is it?
73.96.
Divide by 5?
Yeah. 43 divided by 5
Yeah.
square.
Yeah, no square.
No square. 8.6.
8.6. Okay. And then what did we say the total x was? 4, 5, 6, 7, 8, 9, 10, wasn't it? And the total y was 43? Okay, so what do we get for SXY? 68.8. Yeah? Is that right? This formula doesn't have a square root in it, does it?
4.3.
No, there is no square.
For what?
10 multiplied by 4.3. So it's just 4.
No, the sum of it.
Isn't it? Yeah, oh, you have it right there. Can I see?
Yeah.
Can you write down the formula, please?
No, you have it shown up in your notes.
Yeah, I know.
Oh, sorry, I screwed up. Sorry. It's just, sorry, what was that? 8.6.
6.
Yeah, sorry. Here, it's x times y. Yeah. So that would be 0, 5 plus 22 plus 36 plus 60. Thank you. So if you put that in over 5 and then minus that. Thank you.
It's 7.4.
Final answer? What is it?
Yeah, 7.4.
7.4.
Yeah.
Okay, now let's calculate the OR. So that would be 7.4 over 1.41 times 5.39. I think we're doing 3 significant figures, although we should have done 4. So what do we get here? Well, it's a positive, that's for sure.
It's 0.973697.
97. 97, one more. 36?
Yeah.
So 4 then.
So quite close.
Yeah.
Quite accurate.
I have a question.
Yeah.
So,
So that means that, oh yeah, so vocabulary time. In the exam, guys, in the exam they sometimes ask you to describe this result. So you would say this is a strong positive correlation. They want those 2 words. Strong positive
if the answer is
correlation.
positive.
Yeah.
It could also be a weak correlation. 28.
No, there's only 4 choices, really. Strong positive, weak positive, strong negative, weak negative.
And when do I say?
When it's the word positive.
Well, negative obviously is when you get a minus answer.
Yeah, but weak.
And when strong?
Yeah, they'll always make it clear. You know, you'll get a value like 0.9 or 0.1. So as a rough guideline, just roughly, over 0.5 you can say strong, and less than 0.5 you can say weak. Now, that's only a very rough guideline for the exam. It's not accurate in real life. Yeah, well, you see, there is no statistical rule for deciding when it's strong or weak. The only, okay, I said 0.5, but actually it's lower than this. A lot of times people say it's strong, oh sorry, not lower, let me think.
Over.
More than 0.5?
No, I think you say it's strong when the OR is more than roughly 0.75 roughly, and then it's weak when the OR is less than 0.75. That would be the most common convention I see in statistics books.
Marsky.
No, not marking scheme. Marking scheme, they'll make it very clear. You'll get a value like 0.91 or 0.1. You won't get a middle value.
Like as close as a 1, 0, 4 is.
Yeah.
I have a question.
One sec. Can you just square this, please, and tell me what the R squared is?
0.948. 0.9.
So 94.8%.
Yeah.
So our linear model explains 95% of what's happening.
So it's almost perfect.
Yeah. Now, the reason I chose 0.75 roughly is because in most textbooks you want the R squared to be at least 50%. And I think 0.75 times 0.75, oh, it's not quite 50, is it? What's 0.75 times 0.75? Yep.
0.75 times 0.75
Yeah.
is 0.562.
Okay, so 75 is a little on the high side. Maybe it was more like 70. Anyways, most textbooks want the R squared to be more than 50% before you start saying it's strong. In less than 50, you can say it's weak. However, this depends entirely on the context of what you're studying. Okay? So, for example, Here we're saying more than 0.75. However, if this was sociology, then you would say or is strong once it's more than 0.25.
Or is what?
How much of a relationship there is. Huh? Social science, yeah.
Because the database is pretty big. So if it's 25, but you have lots of.
No, that's not the reason. It's because in sociology it's difficult to establish relationships between two things. So for example, I'll give you some typical values here. Can I scroll down? So, the values I'm giving you are values when you start to consider R squared to be good. Okay, so for example, if you're doing something like physics, for example, you want the R, you won't call the R squared good or strong until it gets to about, oh sorry, this is the subject. Physics, you want to have something like a 0.95 for R squared. Okay? And the reason for this is because in physics there should be no reason for not having a perfect explanation of the relationship between two variables. Okay? Something like medicine, yeah, anything more than 0.5 is good. Okay? Something like a social science, that 0.25 is when you start saying it's strong or is good then. Chemistry would be the same as physics. You'd want like 0.9, something like this. 100 only. Yeah, bio would be the same as medicine. You want a 0.5. Okay. And what other areas might you be studying? Business, yeah, like business, like sales and something like this. Yeah. Again, that would be 0.5 as well. Psychology would be the same as social science, 0.25. Okay. Yeah. Now. Yes.
Teachers work.
And stress.
0.1.
Yeah, no. Strong positive relationship. Yeah. Yeah. Now. Let me think. There's some, okay, so I'll give you another small example here, okay? I think we've talked about this before, but we can see if we can remember. Imagine you have some data here, x and y, and you plot them, and you get a pretty good fit. Maybe you have something like r squared even is equal to, say, 0.8. So it's pretty good. Can we say that x causes y? What can we say about the relationship between x and y here?
Almost should be the same.
Yeah. Huh? Yeah, I mean, but could we say, would it be right to say, oh, x is the cause of y? Like maybe...
Slightly.
Yeah. You're thinking that x has some effect on y, or a lot of effect on y. And it's proportional, yeah.
Isn't on each other, not like just x and y?
Yeah, well this is, okay, so now we're talking. The first problem is, you could have plotted the data the other way around, couldn't you? You could have plotted the y variable, whatever it is, you know, weight or whatever, here, and you could have plotted the x value, height or whatever, here. And you'll have the same type of relationship. It'll be just as good. So you can't say x causes y, because you don't know if it's the other way around. You don't know if it's y causing x. You just know there's a relationship here. So take the example of height and weight. So is it having greater height causes greater weight, or is it that having greater weight causes greater height?
Height and weight.
It's height.
Yeah. So you realise that it actually matters which you put on the x and which you put on the y.
So height on the bottom.
Height on the bottom.
Yeah.
Okay. But there is another problem here. In some situations, you can have a relationship between x and y, but they don't cause each other. And I did give you one example of this before, I wonder if you remember, where you can have a relationship where you have two variables, they increase together and they decrease together, but neither of them is causing the other one to change. That's it, ice cream sales and death from drowning. So as ice cream sales go up, the number of deaths from drowning goes up as well. And as ice cream sales go down, number of deaths from drowning go down. And what was the reason for that? Yes, the sunshine.
So what we call like FBX
Is
equal
there,
to 1.
Yeah, so we have some vocabulary now.
it's only because of the third variable. it's
Exactly, yes, and this is very, very important. Guys, I keep looking over here and you keep talking. Now pretend I'm giving you some information important for your medical career. Okay? So this is very, very important in medicine because you've spotted with this simple example that you can have situations where there's a third variable that's causing the changes in x and y. So in the example of ice cream sales and death by drowning, what was the third variable here? Sunlight, like temperature. Okay. Did the x cause the y? No. And did the y cause the x? No. But if you plot them, will they have a strong relationship? Yeah. And that's because of this guy here. And this is called a confounding variable. It is causing the x and y to change together. It's making it change together. Now this is very important in medicine because often it's the case that you might see patients and they seem to have these two problems together. And you might start to think, well, maybe it's because they have this, it's causing this to happen. Or maybe it's because they have this, it's causing this to happen. But there's a possibility that, oh, there's actually a third thing. So the example might be, imagine before people knew smoking was harmful. Doctors might see, well, these patients have lung cancer and they also have yellow teeth. The patients with yellower teeth seem to have more lung cancer than the patients with less yellow teeth. So maybe lung cancer causes yellow teeth, or yellow teeth causes lung cancer. Well, you're laughing because now we know there's a third thing that's causing both, which is how much you smoke. Okay? But this is the problem in medicine, is trying to separate out. So another more recent example, I think, would be heart attacks and cholesterol. Yeah? Heart attacks and cholesterol. So, patients that tend to have heart attacks tend to also have what situation with their cholesterol?
high.
High cholesterol.
Yeah. But high cholesterol.
Yeah, but do we know that it's high cholesterol that's causing the heart attacks? Or maybe there's some other condition that is making both high. And this is not agreed upon. Okay? Some medical practitioners think high cholesterol is the cause of the heart attack, and some people think it's not. I don't know if Colin has talked to you about this, has he?
Not yet.
No. The only thing that is clear from the Nikita, the only thing that's clear from the research on cholesterol is that patients who had a heart attack, high cholesterol will increase their chance of getting a second heart attack, and lowering their cholesterol afterwards will reduce it. Okay, but it's not clear if for your first heart attack, high or low cholesterol matters. It's only clear for your second one. So if you already had a heart attack, your cholesterol level does matter as predicting your chance of having the next heart one.
Confidence.
Yeah?
Yeah.
But we don't know for the first heart attack if the cholesterol has an effect. So this is controversial because there are people in the UK who would be at an at-risk group of a heart attack, you know, in their 40s or 50s, they smoke, they drink, and they have high cholesterol, and they're recommended to go on medicine that reduces their cholesterol.
But they continue to drink and smoke.
Yeah, but they have the medicine that reduces their cholesterol. But that might not be doing any good if the cholesterol isn't the cause of the heart attack, And of course, you all know that all medicines have side effects.
Yeah.
So maybe they're having pointless side effects and they're not reducing their risk. Okay? So this is all interesting stuff for medical research. And we're only looking at baby stuff today. When you go on for further research, it gets more complicated. Okay? The other thing is, in some situations, the relationship is not linear, but there's still a relationship here, like in this example. Is there a relationship between x and y?
Yes.
Yeah, in fact, the relationship could be perfect. It could be like this. However, if you calculate the r squared, will you get 1?
No.
No, because it only tells you if it's a perfect linear relationship. So this is what I mean as, this is only an introduction to the theory. When you study this further, you can introduce things like a quadratic relationship or other variables other than just x. Yeah?
Will we be studying other relationships?
Not at this level. Not at this level. But first year statistics, they'll have you look at models where there's more than one variable, like there's an x and maybe there's a z, or even z squared or something. Now you think that sounds much more complicated. It's actually not much more complicated. So this actually is most of the difficulty. Okay, so I'll let you practice these for a few minutes then.
Can I ask my question?
Yes, your question. What is it? Well, let me just tell you which ones to try. 4, 5, and 6 would be good to do. 4, 5, and 6. Haza, what's your question?
So, now, for what like we are using these formulas? Like, explain.
We used them today.
No, we used them here and before.
Yeah, and today. Yeah, we used them.
So, what they do, like, what do they determine?
Many things. We can use them to calculate the or, and we can use them to calculate the line.
How to calculate the line? We already calculated.
Yeah.
No, I mean the line. We can't calculate the line without these. Like we can't put the x.
Oh no, you're really supposed to use these to calculate the line.
How I'm gonna use them? The line should be like x and y,
Yeah.
and these are like.
Well, didn't you write down an example? It was the lesson after this. Huh?
No, this is the previous lesson. This is the line of this.
How's that? It's not, oh no. Here it is. Here it is. Here. This is calculating the line of best fit. There's the formula there. Y minus y average equals sx squared over sxx, I think. There's the formula there, the top one.
The one?
Yeah. No, above it.
The one?
Yeah.
So only this formula can calculate the line of best fit, and the rest can calculate the R.
Yeah, no, but you notice that these are used in the line because the line has an S in it.
Yeah, so we have to do this to get the number and we put
Yeah.
But yeah, then how I'm gonna put this number on the graph?
Oh, you can't. They're just calculation numbers. Rough work.
And when the question asks me to draw a graph, do I take these numbers?
Yeah, and
put them
plot
in?
it, yeah.
I'm gonna do the equation.
If they want it. Or sometimes they might just want the graph, you know.
So now we do 1 to 4?
No, 4, 5, 6.